Okay, so if we assume the outcomes are already normal, there is no appealing to the central limit theorem, so we do not need to say as n gets large or for n large enough, we can make inferences with small n. Very small, so it doesn't really matter. I mean, we still get more information if we have more outcomes, but the results that follow apply even for small n. Okay, so let's just look at an example to start. So an example we might want to do. So now these are probably unknown. So mu and sigma squared, probably unknown. So in general, unknown. Okay, so, and we might want to make a test about mu or about sigma squared. So I don't know why it looks. So suppose we want to make a test about mu, for example. We might want to consider, is mu big enough? So we might have a test, for example. A test might be, could be H0, say mu equals mu 0 versus HA mu, say greater than mu 0. Other possibilities are mu less than mu 0 or mu not equal to mu 0, or even mu equal to some other value mu a, or mu in some other range. So could get even fancier. Okay, so to begin, so if this is the null and alternative hypotheses, then we need a rejection. We need a decision rule. We need a test statistic and a rejection region, which will decide between these two. So instead of using the natural estimator for mu would be y bar, but instead of using just y bar, we'll use a transformation on y bar. So we'll let t equal y bar minus mu 0. So the numerator will be positive if y bar is bigger than mu 0, and it will be negative otherwise, over s, the sample standard deviation, over the square root of n. And you might remember from earlier chapter, I think chapter 8 on confidence intervals, if not chapter 7, probably chapter 7 on distributions related to the normal. This is a t-distributed random variable with n minus 1 degrees of freedom if under h0. So if this is the actual mean, so when mu equals mu 0, it has that distribution. Okay? All right, so we let t equal this. And now I want to reject when I have evidence that mu is bigger than mu 0. So this will be when y bar is bigger than mu 0, sufficiently bigger. So when y bar is bigger, t is bigger. So we can also look at a right tail rejection region. And rejection region. So we can also look at a right tail rejection region for the transformed variable t. So this would be t, say, greater than k, where k chosen to satisfy alpha. Okay. All right. Okay. All right. So looks good. So let's just do so I think I'll skip showing you that this is Tn minus 1. Instead, when we get to the slightly different test, I will show the distribution is t-distributed. But for this one, you should look this up if you don't understand. One thing is, you can see right here, it does look like something that's normal, standard normal, only with sigma replaced by s. So it should at least look familiar that it's t-distributed, but I think we did do the proof a couple months ago, but we won't take time to do it now. Okay, so if I'm trying to see what time it is. Okay, so continuing. Yeah, so let's do an example. Suppose we have y vector of outcomes, which is 8, 7, 8, 11, 10, 8, 7, 8. So n is 9. And we'll assume yi is normal, mu sigma squared. And these represent, this yi is inches over 6 feet and represents of NBA forwards. So this is the forward position. I took 9 players. I took their height, how many inches they are over 6 feet. So 6 feet 8 inches, 7 feet, 6 feet 7. And we'd like to do a test to see if it's reasonable to claim that the current NBA forward in the league, its mean height is bigger than 6 feet 8 inches. So our test will be mu equals 8. Remember, this could be less than or equal to 8. We are using the shortcut here, and HA mu, the equivalent way to express it. Mu is greater than 8. Since I really want to claim this, I don't need to fuss too much here, so we're just going to check if we can, under this, if it's reasonable to reject this. There's enough information. So, okay. So let's, now we have the data here, so I can compute t. Do you see that? We have everything to compute t. So there's 2 approaches to do this test. I haven't given an alpha yet, so let's give an alpha. Let's say test this for at level alpha equals 0.05, say. So one thing I could do is just compute, I don't need to find k, but let's find k. The other thing I could do is just find t, and then find the p-value, and then I could discuss what level tests I could reject at, and which ones I maybe couldn't quite reject at. But let's just find k anyway for that level. So if we do that, let's see. So to find k at that level, so I need this to be 0.05. So the t, so I'm going to reject, right? So we reject. So we want to reject. So when H0 is true, so alpha is equal, we want this equal to 0.05, and we want this to be the probability that we reject. Probability t is greater than k, given mu equals 8. Okay. Well, if mu is 8, okay, so if mu is 8, then t, so with mu equal to 8, y bar minus 8 s over n is t with n minus 1 degrees of freedom. This is also 8 by coincidence, right? So this is 8 degrees of freedom. Okay, so this is T. Okay, so that has the T distribution with 8 degrees of freedom. I'm going to draw a picture here of the PDF of T8, crude picture. And we want the rejection region to be a right tail. So K is going to be some value here, such that this area here is 0.05, right? Okay, so this I would do using the computer, right? I did it ahead of time, or a table. So if I look this up, I have K is equal to QT 1 minus, so 0.95. So this gives me the value here that has 0.95 of the probability to the left of it. It's the inverse of the CDF. And I have to tell it, this says quantile, T distribution, 0.95, 8 degrees of freedom. And if I do that, I get 1.86. Okay, so K is 1.86. All right, so now I will compute my T from the sample. So from sample, we have T is equal to y bar minus 8 s over square root of 9, which is 3. I found y bar was 8.77, and s was equal to 1.81 about, which told me that T was about equal to 1.29. So we fail to reject H0 and conclude there is not sufficient evidence based on this sample to claim forwards are taller than at level 0.05 equal alpha. Okay, yes, okay. P-value, if we had done that route, we didn't really need to find K. So note, instead of finding K, you might want to know K if you're going to do several of these, but if you're just doing one, instead of calculating K, we could have found the p-value, which was equal to 1 minus PT. Our test statistic was 1.29, 1.298, and this gives me 0.116, I think. So this would tell me also that I don't want to reject, because it's telling me this much area in here is 0.116, and here's K, and this is 0.05. So since P, the area to the right of the test statistic is bigger than the level of the test, it's telling me that the test statistic is smaller or to the left of the cutoff here for the rejection region. Okay, thanks. Next lecture continues this one.